And so again, we are going to be recording this session today, folks. So let's go ahead and get into our gas heating module number 3 and 4 today. We'll be doing those modules today to kind of round out the gas heating program. And so we'll ask to make sure that everyone can see this first PowerPoint slide. Everyone should be able to see the first PowerPoint slide. It should say the gas heating diagnostic module number 3. Can everyone see the slide okay? Go ahead and unmute your microphone, please.
Yeah, we can see the slide. We don't have the hard copy.
Oh, you don't? Okay. As far as any of the handouts or anything?
Right, and that may have been me. I just assumed that this was all in one.
Okay. Well, what we'll do is definitely still go through the program, but Jill should have sent you some handouts or in a PDF format just to print down so you can have some handouts to kind of follow along. But a lot of what we're going to be doing in module number 3 and 4, you can just kind of follow along on the PowerPoint as well, if that's all right.
Yep.
All right, well, I'll tell you what, team, let's go ahead and get started today then on gas heating diagnostics module number 3 and 4. And so, again, welcome to the program. We sure appreciate the opportunity to train with you today. Some of the things we're going to be talking about specifically are going to be sequence of operation for single and two-stage furnaces. We're going to talk a little bit about safeties and their proper position for normal operation. We're going to get into flame proving and a little bit of the science behind flame rectification, and then normal operation and indoor blower on delays. So in this portion of the program, you can kind of follow along, and as it turns out, a lot of the text fields that I referred to on pages 6 through 13, we kind of breeze over them. I don't read it to everyone. And so by all means, we can go through the sequence of operation and talk about it. I'd rather have everybody understand how that works anyway, as far as sequence of operation. Then you can always download the PDFs, or you can always print those down and review the text fields individually. And again, it's not my style to sit here and read stuff to you. So this is kind of handy anyway, because we have the opportunity now just to talk about how it works. So we're going to talk about proper switch position for a heating call. In addition, we're going to discuss high temperature safety circuits as well as igniter warm-up sequence. We're going to get into indoor blower on delay timing and flame proving. And so all this works together as we talk about sequence of operation. So the first thing that happens in our normal sequence of operation, we're going to have a thermostat call for heat. And so what happens electrically, and again, if you want to just make a note of this in your handouts or future handouts, basically pages 6 through 13 will be the areas that we're going to be talking about. So on a normal call for heat, what's going to happen, you're going to have 24 volts going to the thermostat all the time. And when the thermostat calls for heat, it's going to electrically connect between R and W, Once we have a W call, in other words, we're calling for heating operation to the furnace, what's going to happen, the first thing is the unit's going to go out, it's going to check all the safeties. And so when we get a W call, and this happens instantaneously, it takes longer to talk about than it actually works on the furnace. But so what happens is the thermostat calls for heat, and it goes out and checks all the safeties, and the pressure switch has to be open electrically. So if all the safeties are closed and the pressure switch is open electrically, what happens is we then start the induced draft blower motor. Once the induced draft blower motor starts up, it's going to close the pressure switch electrically, and then we'll continue with our sequence of operation. Once we close that pressure switch and we confirm that we have venting, we're going to close that pressure switch, and then that switch is going to close at a particular negative pressure. Now, this is important we understand that it's a negative pressure switch, so it's going to be sucked closed by the induced draft blower. And we'll talk a little bit later on how to check that switch and how to test that switch with a magnehelic gauge or digital manometer. So once that switch closes and we confirm venting, we then start our ignition warm-up sequence. Now this is going to be 17 seconds. And so we're going to put 120 volts AC to the hot surface igniter, and it's going to warm up for 17 seconds. After 17-second warm up, we're going to open the gas valve. Now this is important. Once we open the gas valve, we're going to once we energize the gas valve and we open the gas valve mechanically, we're going to start feeding gas into the burner assembly, and the hot surface igniter is going to ignite the fuel mixture. Once we get flame, two things have to happen. Number one, we have to have flame sensing with our flame is being proven with our flame sensor. And once we have flame sensing, we then shut the hot surface igniter off and we start our indoor blower on delay timing of 30 seconds. Now that 30 seconds is preset at the factory. We can't change that. And so there's nothing we can do to change that. Now we can field adjust the off delay timing once the call for heat goes away, but the on delay timing is factory set. So the hot surface igniter shuts off once we have flame proving, and we start the indoor blower on delay. Once the indoor blower on delay timing has expired, the indoor blower comes on and we start distributing heat throughout the conditioned space. That's how it works. So one more time as a quick summary, we get a call for heat from the thermostat. Once we have a W call on the control board, it goes out and looks at all the safeties to make sure all the safeties are closed electrically. And the pressure switch has to be open. Pressure switch has to be open. Once we confirm that, the induced draft blower comes on and it sucks the pressure switch closed. Once the pressure switch closes, we start a 17-second igniter warm-up sequence. Once that 17 seconds igniter warm-up sequence has expired, we then open the gas valve mechanically and we feed gas to the burner assembly and we ignite the fuel-air mixture. Once we establish flame, two things happen. Number one, the igniter shuts off. And number two, we start our indoor blower on delay timing. Once the indoor blower on delay timing expires, the indoor blower comes on and we're now distributing heat throughout the conditioned space. Any questions or comments on that first sequence of operation as we start our furnace up? Any questions or comments?
Nope.
Okay. Normal shutdown occurs when the thermostat is satisfied. It breaks that W signal to the furnace. The furnace then, as soon as it loses flame proving, it goes through a shutdown sequence. The induced draft blower will continue to run about 10 to 15 seconds, and the indoor blower starts its off delay timing, which is field selectable from 60 to 180 seconds. Once that off delay timing is over, the indoor blower shuts off and the unit goes back into standby mode, ready for the next call of heat. So that's normal sequence of operation for a single stage unit. So again, is there any questions or comments on that sequence of operation? Everybody good? All righty. Well, sometimes this is something very unique about the Champion furnace, in the fact, unlike some manufacturers that will take their second stage pressure switch and just bring on their second stage gas valve strictly by the pressure switch, we do it a little bit differently. So on our two-stage product, our two-stage sequence of operation, it's identical to the single-stage operation for that first function. So here's what I mean by that. So if I get a call for W1 first stage heating on a two-stage product, it's going to go through the same sequence of operation. It's going to see a W1 call from the thermostat. It's going to go out and check all the safeties just like we did before. It's going to start the induced draft blower, but now wait a minute. When we start the induced draft blower, we're going to actually start on high fire or high speed. And what we're going to do, we're going to suck both the low fire and the high fire pressure switches closed. Now, the reason we do that, even on first stage, we want to exercise those switches because we have found that it gives you a lot more reliable product if you exercise those switches each time. So the end result is this: we check all the safeties, we start the induced draft blower on high speed, we suck W1 and W2, in other words, we suck both pressure switches closed, and then we start our igniter warm-up sequence. 17 seconds later, just like before, we open the gas valve, but because it's a two-stage product, we're actually going to exercise and open that gas valve on high fire. So every single time on a two-stage product, we fire the furnace on high fire to exercise the gas valve and the pressure switches. So back to the sequence. Once we open the gas valve on high fire, we then establish flame. Now, once we establish flame and we have flame proving, we have a 30-second window before the indoor blower comes on. Now, during that 30-second window, before the indoor blower comes on. If we only have a W1 or first stage heating call, what happens is the gas valve backs off to first stage fire rate, and the induced draft blower slows down to first stage operation, and the second stage pressure switch opens. And now 30 seconds later, we start our blower on low fire or on our first stage, and we're distributing heat throughout the conditioned space on first stage. Now look what happens if we have a W1 and a W2 call together. Let's just say it's cold in the space, or maybe the homeowner had the thermostat set in setback. And if the thermostat simultaneously calls for W1 and W2 together, so in other words, we're calling for first and second stage heating together. What happens in that scenario is the control board sees it has a W1 and a W2 call together. It goes through its normal sequence of operation. Again, it looks at all the safeties, make sure all the safeties are closed. It then starts the induced draft blower on high fire, just like before, and it sucks both pressure switches closed. Once those pressure switches are closed, we then start our igniter warm-up sequence of 17 seconds. 17 seconds later, the gas valve comes on high fire, W1 and W2, second stage fire rate, and we establish flame on high fire. But now wait a second, because we're calling for W1 and W2 together. In other words, we have a first and second stage call together. During that 30-second time frame of the indoor blower coming on, instead of doing something, it just stays in high fire. Because remember, if we had a single stage call, it would back off to first stage during that 30-second blower on delay. But if we have a W1 and W2 call together, in other words, the thermostat's calling for first and second stage together, what happens, it just stays on second stage. And so we then, 30 seconds later, we start distributing heat throughout the conditioned space on the second stage blower speed for second stage heating. So this is something very unique about the Champion furnace, is that every single time we fire the furnace, we fire it on second stage, and then if it's only a W1 or first stage call, we back off to first stage during that 30-second time delay of the indoor blower. If it's a W1 and W2 or a first and second stage call together, we just stay in second stage to bring that, to bring the blower on second stage after that 30 seconds. So the real neat thing about this whole sequence of operation on two-stage product is, for reliability and for longevity, we exercise every single time. We exercise the induced draft blower on high speed. We exercise the gas valve on second stage. We exercise the pressure switches on second stage as well. And what we've found in our testing facilities and our torture chambers, that if you exercise these components on every single call, you get a more reliable product. And again, unlike some of our competitors that don't do that, they have premature failure sometimes of those second stage pressure switches and stuff, because they're not using them all the time. So it's actually better to exercise those components. So that's kind of something unique about our Champion furnace that we do to increase reliability and longevity of the product. Any questions or comments on that basic sequence of operation for two-stage product if we have a single stage and a second stage call? Any questions on that?
Nope.
Everybody good? Well, all that stuff I talked about will be found in the text fields of the handouts. If you get the opportunity to print those down, you'll be able to check those things and learn a little bit more about it and read the text kind of at your leisure or when you have time to do that. Okay, so at this time we'd normally take a little break, but because we're kind of breezing through and we haven't had a lot of questions or comments, we'll just go ahead and pick back up on module number 4, if that's okay with everybody. And so at this time, let's go ahead and jump into the final module of our gas heating diagnostics, module 4. And in this portion of the program, we're going to talk about testing that vent pressure and the proper use of tools to check that vent pressure. We're also going to get into talking about checking gas pressure for both single and two-stage furnaces. And we're going to talk about how to measure flame current and review the science of flame rectification. So some of the things that are important about testing vent pressure. Now, this is something we recommend that the technician does every year on his yearly clean and check, because vent pressure can degrade over time because the induced draft blower starts getting some wear on it, or perhaps you've got a vent pipe, especially like on a 95% furnace, it's a condensing style furnace. That vent pipe, might have some water lying in a low area of the pipe, or you might have critters have put pine cones or built a nest or something in that vent pipe. So I think it's important that every year, we confirm that the vent pressure on the furnace is proper, because that's really your safety. Your venting is a very, very important part of your clean and check every year. So we're going to talk about checking that vent pressure and how to attach the test hoses, calibrating the Magna-Healy gauge. We're going to talk about actually measuring vent pressure and then confirming proper vent size from the appropriate tables. So you'll find that in your handouts, if you get those printed down, that you'll have some vent tables. They'll tell you what size pipe you have to have on those vent tables. Now, one of the important things we have to remember about this process of testing vent pressure, there's a lot of different tools that you can use to check vent pressure. Basically, we're going to be looking at fractional inches of water column vent pressure. So for training today, we're going to be featuring a Magna-Healy gauge. A Magna-Healy gauge is a very accurate gauge. It's an analog type of gauge. It just moves a needle. And we're going to use that for training today because it's easy to look at. However, if you have a digital manometer, that works perfectly fine as well. So a digital manometer or an inclined water manometer or a Magna-Healy gauge are all acceptable tools. Now, this is really important. Please make a note of this. You cannot use like the regular old YouTube manometer. You can't use the old YouTube water manometer because it's not accurate enough. Now, if you have the inclined water manometer that lays on the side, that has very, where you can read fractional inches of water column, that's fine. But we find that most technicians are either going to carry a Magna-Healy gauge, like what we're going to be talking about today in our presentation, or a digital manometer. And so either one of those gauges will work fine, because remember, team, one more time, we're going to be checking fractional inches of water column, and the old YouTube manometer that you take gas pressure with is not going to be adequate for checking vent pressure. So the first thing we're going to do, we're going to look at the vent pressure switch that we're going to be testing. And so every one of our pressure switches on our Champion furnaces, if you look at them closely, you're going to find that they'll have some hoses hooked to them and stuff like that. But you're also going to find that there's going to be a data plate on that pressure switch. So if you find the data plate or the data tag on that switch, it's going to tell you some information. So you don't have to look at any big, complicated charts or books or anything like that. Just go to the pressure switch. The pressure switch that you want to test, just go to that pressure switch, look at the data tag, and you're going to find on that data tag there's going to be a operating pressure or a closing pressure of that switch. So you'll notice in our example here, that the closing pressure or the operating pressure of this switch is a minus or negative 0.50 inches of water column. Again, a negative 0.50 inches of water column. Please write that down and remember it, because as we start doing some examples of testing a vent pressure switch, we want to remember that switch is going to operate at negative 0.5 inches of water column. So again, once you identify the switch you're going to be looking at, what you're going to do, you're going to remove the hose from that switch. Now that switch is going to have some hoses going to it. Just remove the hose that goes to that switch and tee it in with just a hose barb type of tee. A plastic tee is fine. And by the way, team, I recommend that you put yourself together a little gas box. That's what I used to have when I was in the field. I actually had a little tackle box that I had a bunch of little tees in there and some extra hoses and stuff like that. And you can go down to your automotive store and you can buy all these little tees, at the automotive store, or go to Lowe's or Home Depot or one of those, big name hardware places. And they've got all these little cute little hose barbs and little plastic tees and nylon tees. And that's what I had. I had a whole box of that kind of stuff and hoses and things like that, that I bought at the automotive store, little pieces of vacuum hose. And so put together a little little gas box is what I recommend, because that way you've got all the stuff you need right there to do all this. So you're going to remove that hose from the pressure switch you're going to be testing, and you're going to tee it in, and you're going to take the other side of that tee and you're going to take it over to your MagnaHelic or your digital manometer. You're going to tee that in, and you're going to bring that hose in, and you're going to hook it up to that digital manometer or MagnaHelic gauge. And if you're using a MagnaHelic gauge, you're going to want to make sure it's setting upright like we have in the picture, and you're going to calibrate it to 0. If you have a 0 function on your digital manometer, go ahead and 0 it, before you start the furnace up. So you're going to hook this hose up, and there's that hose that's connected to the T on the pressure switch. And then you're going to start the furnace. Once you start the furnace, you're going to observe the vent pressure on that switch that you're testing. So you start the furnace and you let it go through its normal sequence of operation and let it start running normally, and then check the vent pressure. Now, team, remember, this is negative inches of water column. So in our example, we have in this first example, we have a negative 0.85 inches of water column. Now remember, team, it took from the little data tag that we saw on our pressure switch, it takes a negative 0.5 to operate that switch. Well, here in our example, our furnace is actually sucking down our venting system with our induced draft blower and the vent pipe that's hooked up to it and so on. Is able to maintain a 0.85 inches of water column. So we're in good shape. We not only close that switch, but we're also maintaining a positive vent pressure, for safety and for combustion efficiency. Any questions or comments on this first example? Everybody good? All right, quick audio check just to make sure I haven't lost everyone.
We're here.
Okay, fantastic. All right. I appreciate you doing that too, because when everyone's kind of quiet, it's like, okay, I make sure I haven't lost anyone. All right, so let's do another example, team. So here we go. So in this second example, we see it's on a different, maybe a different furnace or what have you. But in our example, we needed a negative 0.5 to close the switch. And in the second example, we see we've got about a negative 0.65. So the furnace is operating. Maybe this is a little different service call where we have a longer vent pipe, or maybe an extra elbow in the vent pipe or what have you. So it's a little different pressure. Now, team, this is really, really important to kind of remember. You always want to make sure, and this is just a rule of thumb, and I don't like giving a lot of rules of thumb because it can vary so much, but as a general rule, if the vent pipe is the proper size and you haven't exceeded the length in the venting tables, typically our Champion furnaces will close that pressure switch with enough pressure to close the switch plus about 25 to 50%. Now that's just a general observation, a field observation. So if it closes at 0.5, if the vent system's in good shape and all that kind of stuff, a 0.75 or 0.8, something like that would be about a normal vent pressure. Now I've seen some of our furnaces with really short vent pipe and very few elbows in the vent pipe actually close that pressure switch at a particular value. In our example, a 0.5 is where it closes, but I've seen it sucking down almost 1.0 inches of water column. So what I'm trying to say is that, based on the length of the vent pipe and based on all of that and the number of elbows and the size of the vent pipe and so on, typically you want to be looking for about 25% more, up to about half or 50% more than the closing pressure of that switch for a little margin of error, a little margin of safety. So you can see here 0.65 is still in good shape, but at the same time, it's not quite as good as that 0.85 that we had in our previous example. So the vent pressure is a little bit lower here, where it's still giving us reliable operation, but we want to kind of watch that, because if it's degraded from the last time we checked it, we need to make sure our vent pipe is clear and we don't have any critters haven't put any haven't built a nest in the vent pipe, or put mud daubers haven't got in there and obstructed the vent pipe. You get the idea. So So this is, again, one of the reasons we recommend that every year we check our vent pressure to make sure that it hasn't changed or degraded from the previous year. And so I recommend to all of our technicians that attend this training to go ahead on your service ticket, write down your vent pressure on the customer's ticket of the furnace that you observed that year. Same way with flame current, which we'll talk about in a little bit. Write down the flame current, what it was, just on the service ticket, so you can keep track of it. So over time, or over the next year or the next couple of years or whatever, if you start seeing a degradation, or that vent pressure starts degrading, or that flame current starts degrading, at least you'll have a reference point. Now that's just a field tip and lots of years of doing service. So again, 0.65 negative, we're in good shape in this second example. In our final example, we see that for some reason we're not closing that pressure switch like we're supposed to. Now there's lots of reasons. In our example, we only have a 0.3 inches of water column and the vent pressure is low. Now, one of the things we're also going to notice is on the furnace, we're going to get a 3 flash code, a 3 flash, because a 3 flash means that the pressure switch is supposed to be closed, but it's open. Now, there's lots of reasons it could be open. The biggest one is that you've got water. If you've got a low spot, or if you have a sag in your vent pipe, you could have water laying in that vent pipe and acting like a trap. If it's been a full year, or it's been over a long summer since the unit's been run, it's possible some critters have made a nest up in the vent pipe. And then, of course, if the furnace has got some age on it, it might be the induced draft blower is starting to degrade and not being able to suck quite so hard. So one of the things we always recommend is, just think it through, because what it is that vent pressure and that vent safety switch is there to tell you that you don't have, or you do have, either way, adequate venting. So you'll notice again the red LED, it gives you a 3 flash, and it tells you that we're having a problem with the venting or the vent pressure switch. And so we've talked about some of the things we should check: the vent pipe, make sure it's clear, make sure the induced draft blower is working okay, and then finally you might just have a bad switch. But this is why it's really important, in my opinion, to actually measure your vent pressure. Don't just automatically assume, well, I got a bad pressure switch. Measure that vent pressure and see what's going on with it. Now, the final thing that I'd like everyone to think about, there's one other condition that'll cause a low vent pressure. And I saved it till last because I wanted to talk about it till last, because it's the most unlikely thing. However, if you have a cracked heat exchanger, you will not be able to pull your vent pressure down like you're supposed to. So those are the top 3 or 4 things. The vent pipe is obstructed, the induced draft blower is degrading or just wearing out, and or you might have some debris in that vent pipe. And if it's a brand new installation, it could be the wrong size vent pipe, or maybe the vent pipe is too long. And then finally, if this unit's been in service for a while, it could be a cracked heat exchanger, which is the most unlikely thing, but that's all part of your vent safety. Any questions or comments on testing vent pressure and some of the things we'd check for if we had low vent pressure? Any questions or comments?
Nope, we're good.
Okay, well, fantastic. All right. So again, check your venting tables and some of the things that we've talked about. So at this time, team, let's talk a little bit about gas valves and checking that pressure on the gas valve. Some of the things that we're going to touch on specifically are some of the gas valve features that we have on our Champion furnaces: attaching hoses to the gas valve, single and 2-stage valve adjustments, and measuring inlet and outlet gas pressures. So as we take a look at our gas valve that we typically use on our Champion products, now on our gas packs, you'll see that we have a little different configuration on the gas valve sometimes based on the size of the gas pack. But this is a very common type of gas valve that we have on our Champion products. You're going to notice that there's going to be a post on the gas valve body itself for pressure measurements. And so you no longer have to have a bunch of hose barbs and all kinds of fittings. That you basically are going to need a little adapter So you can slide that hose over that little port on the gas valve, and you're going to need an Allen wrench to open up that little gas valve fitting. So as you take a look at it, you're going to have an inlet post on the front side of the valve, and you're going to have an outlet post on the back side of the valve. Now, team, you guys do what you want to do, but what I like to do when I check a gas valve, I like to take the inlet pressure and the outlet pressure together, because I like to see what the gas valve's doing. Now, it's perfectly acceptable just to take the inlet pressure to make sure we have proper inlet pressure, and then check your outlet pressure separately. That's fine. But what I like to do is I quite often will take like a digital manometer, and I'll put it on the outlet gas pressure so I get a real accurate reading. And then on the inlet gas pressure, I'll use like the old YouTube water manometer and make sure, you know, that I fall within a range. You know, for instance, natural gas should be somewhere between about 5.5 to 7 inches of water column. And you can resolve that easily with the old water manometer. But on the back side, or on the outlet pressure, I like to use a digital manometer because it gives me a little more accurate reading. You know, because if my specifications call for 3 or 3.5 or 3.2, I can resolve that a little bit easier with a digital manometer on the outlet pressure. But on the inlet side, you know, if the range is, you know, 5.5 to 7, well, that's easy to resolve that with just a water manometer. So, but that's just a habit I've developed over the years in my service history. I like looking at inlet pressure, and I like looking at outlet pressure at the same time with two different instruments, just so I can see what that valve is doing. In addition, if you do a lot of propane work, it's real nice to know, you know, what kind of pressure you're getting off that tank, especially if you've got a water heater running, or if you got the stove going, and so on a propane system, because sometimes you can get you can drop below your minimum on propane if you've got more than one device running in the house. So again, it's just one of the reasons that I like looking at both the inlet and the outlet at the same time, having done a lot of service work in rural areas of our country that were on propane. That's just a habit I developed, and that's how I like to do it. So by all means, do like you want to do. So that's just a little field tip. Looking at the inlet and the outlet together is just a good little field tip, in my opinion. You'll note that the tubing slides right over that post, and you don't have to have an extra fitting to read gas pressure. So as you take a look at the gas pressure for single stage, if you had your little handouts there, pages 30 through 31 would describe those gas pressure settings. But to actually take that gas pressure setting, what you're going to do, you're going to remove the cap from the gas valve to adjust the pressure. This is on a single stage valve. You'll then loosen that little Allen screw about 1 turn, and then slide your hose over it, and then turn the gas back on to read your inlet pressure. And then there you'll find that there's the outlet pressure to your manifold. Again, you'll just loosen that little Allen screw about 1 turn, and then slide your hose over it, and then turn the gas back on. Then you'll be able to read those pressures on that single stage valve. And then underneath that brass cap, you can adjust the pressure. Now, it should be noted, team, on a two-stage gas valve, you'll find that information on pages 32 through 33 on your handouts. You're going to have 2 brass caps, one for the low fire, one for the high fire. And it should be noted that on some gas valves, you're going to have to change a spring underneath the high fire for propane conversion. Please make a note of this as well while I'm thinking about propane. I recommend that when you do a propane conversion, that you plan on adding stainless steel burners, because the stainless steel burners are optimized for propane operation. Now, it'll work with the standard burners that come with it on propane, but we find that most of our contractors report that based on the quality of some of the propane they get, you know, they can have more corrosive effect and more water and more condensate being generated with propane. And if you look at the chemistry of propane, you'll see that that's why it's going to have more water content when it burns, or, you know, more steam, more water, if you will, in the combustion process, more steam in the combustion process. And so most of our contractors find that stainless steel burners last a lot longer and work better. So we recommend that if you do a propane conversion, go ahead and plan on using stainless steel burners because they are optimized for propane operation. So anyway, again, on some gas valves, you're going to have to change the spring under the high fire for propane conversion. Once you do that, it's very, very important that you have to adjust your gas pressures for the propane. I know that's probably an obvious statement, but we've actually had some field reports where the contractors didn't know they had to double check that gas pressure. And so this is important. This is the proper sequence of checking the gas pressure after you put the spring in on propane conversion. So what you're going to do, you're going to call for W1 and W2 together, and you're going to call for high fire, in other words, and then you're going to adjust your high fire first. You then call for W1 and adjust low fire. So that's an important sequence of operation. You change the spring on a propane conversion. You then call for high fire operation, W1 and W2 together on a two-stage product, and you adjust your high fire first. You let the furnace stabilize, you adjust your high fire. Then you back off to low fire, W1, and adjust your low fire second. Any questions or comments on what we need to do for propane conversion and some of the tips as far as taking gas pressures and doing a propane conversion? Any questions or comments on that?
We're good.
Everybody good? All right. Okay, so again, when you're testing gas pressure, you can't do what you want to do, but I really like looking at the inlet pressure and the outlet pressure together. And even though I'm showing a digital manometer on both of these on the PowerPoint slide, it's perfectly acceptable to use like a water manometer on the inlet, because oftentimes you'll see our specs might be, like I said, from 5 to 7 on natural gas for the inlet. So you can resolve that easily with the old water manometer. But I really like a digital manometer on the outlet through the burners, because if the specs call for 3.2 or 3.5 or whatever the case may be, I can resolve that better by looking at a digital on the outlet. So do what you want to do, but that's just a little field tip, and that served me well in my 45 years so far in this career. All right, team, at this time, we're going to go ahead and talk about measuring flame current. And it really is a very critical part of every diagnostic service call. This is something that I think every technician should do every year when he does his clean and check, is to double check that flame current, because flame current is your safety, and it's a proving circuit. It proves that the flame is coming on, and if you lose the flame, or if you don't sense flame, or if something's going on with the furnace and the gas valve is stuck open, it's going to be your flame current that's going to be sensing that flame. So it's a pretty important thing, and it's important too that you have the tools necessary to check that. So we're going to talk about flame rectification and the science behind it, and then actually measuring flame current on our Champion furnaces. So the first thing I'd like to talk about is what is flame rectification and how does that work? So basically what it is this: anytime there's power to the furnace, there's going to be an AC voltage being applied to the flame sensor. Now, it should be noted that AC voltage is line voltage driven. And I didn't stutter. I mean, we're talking 90 to 120 volts on that flame sensor. However, it's important that we understand anytime there's power to the furnace, there's going to be power to the flame sensor year round. The other thing that we need to know is that flame sensor, even though it's line voltage driven, it's got AC voltage on that flame sensor, it's an extremely high resistance circuit. So if you touch the flame sensor with the furnace plugged in, it's not going to shock you. If the flame sensor gets shorted out against the burner, or gets shorted out against the cabinet, or bent over and touches something, it's not going to burn anything up, because it has an extremely high resistance. We're talking into the hundreds of millions of ohms resistance. So even though there's 120 volts there, or close to 120 volts, line voltage driven, there's no current flowing through it. So it's still a safe circuit. You'll also notice that on our Champion product, it's the unit, or more specifically, It's the device on the furnace with a single purple wire. It's got a single purple wire going to it, and it's got AC voltage on it all the time. But there's no current flowing because there's no flame present. Now watch this. When we build a fire or when there's a flame present, what happens is that AC voltage actually passes through the flame to chassis ground. This is why it's so important for flame sensing to have a really good, solid, clean ground on the furnace. As a matter of fact, the number one cause for low flame current is poor grounding on the furnace. So if you got a brand new furnace in an old home and you got a lousy ground in the home and it's not sensing the flame, it's because you have a bad ground. And so it's important that you've got a good solid ground from the furnace all the way to the power panel, all the way to earth ground. It's really important. So if a flame is present, what's going to happen is the flame is going to rectify or convert that AC voltage into a pulsating DC voltage that's going to report along the ground plane. That's why grounding is so important. It's going to report on the ground plane or the chassis ground back to the control board. It sees pulsating DC on the ground. It knows there's a flame present. So that's how it works. Basically, AC voltage goes through the flame. And because of the characteristics of the fire itself, the ionization of the flame itself, it actually converts or rectifies. It's an electronic term. It rectifies. It converts or rectifies that AC voltage into a pulsating DC voltage that they dump on the chassis ground. The control then sees that pulsating DC and it knows the flame is present. And so when it sees that pulsating DC on the ground, it knows the flame is present, and it allows the gas valve to stay open and continues a furnace operation. Now remember, again, I know I said it before, but let me stress it one more time. A good, solid, clean ground is required to maintain flame sensing, and polarity has to be correct as well. So in other words, the power coming into the furnace, you've got a black wire and you've got a white wire, a hot and a neutral. If those are backwards, if the power is hooked up backwards on those, what will happen is going to affect the flame sensing circuitry. It's not going to burn anything up. As a matter of fact, a lot of times the furnace will start up and run for maybe 7 or 8 seconds and then it locks out on no flame sensing. And so it's important the polarity is proper as well. So grounding, number one cause for low flame current. Probably the number 2 cause is a dirty flame sensor. And so a lot of technicians, they'll take that flame sensor and they'll clean it. We recommend that if you're going to do that, go ahead and use like a stainless steel wool that you can buy at the grocery store, or Scotch-Brite. Do not use sandpaper, because if you use sandpaper, you can get little pieces of sand embedded or stuck onto that flame sensor rod. And the very next time you put it in the flame for sensing, that sand can actually melt into a glass type of component. So that's what glass is melted sand. So we recommend that you always use Scotch-Brite or stainless steel wool for your flame sensor. To clean the flame sensor, do not use sandpaper is what we recommend. Any questions or comments on the science of flame rectification and how that works? Everybody good?
We're good.
All righty. Well, back to measuring flame current. Team, you recall in module number 1 and 2, we talked about a flame current pad on the control board. So every one of our champion furnaces features on the control board a flame current pad. And what happens is that little flame current pad, we don't have to have any special meters anymore. All you have to have is just a normal voltmeter, volt-ohm meter, like what the technician probably has on his truck anyway. And he's going to set it up for voltage DC volts. And then he's going to call for heat, W or W1, and let the furnace establish normal flame. Once that furnace establishes normal flame, he's going to take his meter to DC volts, and he's going to go to a low scale. When I say a low scale, if he can scale it, typically it's going to be like 5 volt DC. Then you're going to measure DC volts on that flame current pad. Now remember, team, 1 volt DC on your meter is equal to 1 microamp flame current. And so that little flame current pad is a really, really nice little service feature on our Champion furnace controls. You don't have to have a special meter anymore, just a plain Jane voltmeter. Set it on DC volts and read DC voltage on those 2 little spots right there on the flame current pad. 1 volt DC equals 1 microamp flame current. Now it should be noted, the flame current has to be above or should be above 1.5 microamp. As a matter of fact, if it's below 1.5 microamp, it's going to generate an amber flash code telling you that you have low flame current. Now maybe write this down. 1.5 is where you start generating, anything below 1.5, you start generating an amber flash code that's saying, hey, I've got low flame current. Typical flame current should be about 3.5 to 4. About 3.5 to 4, and that's assuming you got a clean flame sensor and a good solid ground to the furnace. 1.5 is where you start generating that amber flash code. If it's below 1.5, you're going to get an amber flash code saying, hey, I'm getting low flame current. Now, please write this down. At 0.1 microamp flame current, it locks the furnace out. So there's lots of room there, basically, before you actually get a lockout with flame current. So 3.5 to 4 is a typical flame current range if everything's in good shape as far as the flame sensor and the, good grounding and so on. 1.5 is where we start generating an amber flash code, and then 0.1 is where we actually lock out for low flame sensing. Oh, back up. So is there any questions or comments on measuring flame current and what tools we would use to measure flame current?
Nope.
Okay. Well, team, any final questions or comments? That concludes our session, module number 3 and 4 in our gas heating program. And we actually did it in a little under an hour. It normally takes about an hour to an hour and a half, but we didn't have any questions. Let's take a minute just to open up the floor right now. If anyone does have any final questions or comments before we secure for the day on our training program. Like I said, I know we kind of breezed through, but at the same time, we don't want you to conclude today without asking those good questions if you've got any good questions or comments.
We're good here.
Well, I'll tell you what then. On behalf of our host and Jill, did you get a chance to train us today? Our training coordinator at Wind Supply. I think she was going to be out today, but on behalf of Jill and her team that have been instrumental in getting this all set up, and from Johnson Controls and your Champion team, thank you for training with us today. And I look forward to training with you again someday in the future. So if there's no further questions, have a great day, and we'll see you next time. Thank you.
Thank you.